Okay, here we go. Chapter 2, derivatives, the big ideas. And so calculus is a limit machine. We can take some pre-calculus math, like the slope of the secant line, and apply something, the concept, not just something, but the concept of limits to come up with a calculus formula. So let's look real quickly at this secant line. I am using x as because obviously if we use x and not a number, this can make sense. If this point's x value is x, then its y value is f of x. And we're going to use delta x to indicate an additional value added on. So delta means change of x. So this second point right here, the x value is x plus this change in x. And so then the y value would be f of x plus delta x. And if you use our slope formula, we get the slope of the secant line. And so let's go ahead and apply this idea of something getting closer and closer. We're approaching something closer and closer. And as we're approaching, our distance between those two things is getting smaller and smaller. So delta x is going to become smaller and smaller. I'm pulling in the x closer to the x plus delta x. If you're looking at the x-axis, we're going to make delta x even smaller. Hope you appreciate the time I spent making these, because I really love seeing the x get closer and closer and watching the slope of the secant line become closer and closer to what the tangent line, the slope of the tangent line would look like. So what have we done? We took the pre-calculus math, which was the slope formula, and we said, hey, what happens if we take the slope formula of a secant line and have delta x approach 0? If delta x is getting smaller and smaller, and so it's approaching 0, then we end up with the formula for the slope of the tangent line. All right, we also know this as a definition of the derivative, because this is the what we also say the long way to find a derivative. So I just wanted to show you guys that, so that if you haven't seen it before, you do have an appreciation for where the derivative was derived from. Okay, so what we're going to do in this video to make it shorter is I'm not going to work through things. I'm just going to show you the work, and then you can pause if you need to remind yourself of what, so you can remind yourself of what it is that you learned last year. So here we go. Find the slopes of the tangent line to the graph of f of x equals x squared plus 1 at two certain points. And so they're not asking explicitly in the directions, but they will on the test ask you to find it using the definition of the derivative. So just reminders to the left that remember to add a delta x to every x that occurs in the function. Don't forget to distribute that minus sign. This is where people make a lot of mistakes. They forget to distribute that minus sign to that second term, and then we end up with the derivative. If you need to pause this and look over the steps, go ahead and do so. I'm moving forward, and here we go. Then we learned last year when we did chapter 2, we learned about the power rule. And so we also learned as we were doing derivatives that when we look at the initial problem, we're going to go ahead and rewrite it, because we need an exponent. A root isn't going to help us when we're taking the derivative, so we need to rewrite, then take the derivative, then simplify. And so that's example 2. And once again, if you need to pause and look this over, go ahead and do so. The purpose of this video is kind of to reach all audiences, those that remember most everything and those that remember most nothing. I don't know, is that grammatically correct to say? So we are still on section 2.2, basic trig derivatives. You need to know that, and we'll add on to those in a second. So then we move on to some really important things. We are still looking at section 2.1. Was this 2.2? Okay, so this is probably also 2.2. So here we go. The slope of a secant line is just what we consider the average velocity. The slope of the tangent line is actually instantaneous velocity. There are different ways to write the derivative. Make sure that you're comfortable with all those. Remember that when looking at a graph, there's no derivative at a sharp turn. So remember that. Also, don't forget that the blue line is still considered a tangent line at the pink point, even though it does cross through the curve again. These are examples, these are examples of graphs that always have negative derivatives. And this is important because it doesn't work in its converse. Differentiability implies continuity, right? A function's differentiable at a given point or across a different interval. Then it's also continuous at that point or over that interval. But I wanted to remind everybody the opposite's not necessarily true, because we're looking at this absolute value graph. It is continuous everywhere continuous, yet it's not differentiable at that sharp turn when x equals 0. So remember, both of them are, it's not, the converse is not true. If it's differentiable across a certain interval, then it is continuous, but the reverse isn't true. All right, so let's move on. And we've got, as we move through the chapter 2, let's see if what section we're in, 2.3. As we move through chapter 2, we see that we have more rules. We've got the product rule, the quotient rule. We're also given more trig derivatives. I know you had to memorize them last year when you did them in Honors Pre-Calc. Same thing here, right? You're going to be memorizing them. Let's check on. We're still going, which is good. And then I think that, when we get to the higher order derivatives in this section, it's nice to remind ourselves that our original function is what we call the position function. And then when we take that first derivative, we're actually finding the velocity. We take that second derivative, we're finding how fast that, the position function, when we take the derivative of the position function, we're finding how fast we change from position to position, so that's velocity. And then we take the derivative of the velocity, it's saying how fast does velocity change, so that's acceleration. And then I'm just going to pretend that I understand what the third derivative stands for, jerk function, and then the fourth derivative, impulse function. Probably your physics teacher can explain what those mean, but that's what we find when we're doing our higher order derivatives. Oh, also, isn't this cute? I've never seen this before. When you're taking the quotient rule, the high over ho. I don't know. If that works for you, that's a fun way to memorize it. I included that. I've never seen that before. Okay, and so these are just some reminders that a lot of times when we see, like for example, this problem here, we're asked to take the derivative of a given function, that it looks like we would, right here, be dealing with using the product rule, but instead we can actually distribute and keep simplifying and then take the derivative. And so I wanted to show you both ways, because guess what? Your choice. Whatever it is that you want to do, you end up with the same answer. So same thing, here's another example of a function we're asked to take the derivative of, and you can either simplify then take the derivative, or you can actually use this quotient. Yeah, it's a quotient, so you're going to have to use the quotient rule, which, it's okay, we end up with the same answer. I just want you to know that it's okay, take a derivative the way it makes sense to you. And I think I pointed out of looking at this, it's the hardest part of calculus, the algebra. For some of you, yes, that is going to be true. So once again, pause if you want to look at this work, just to remind yourself the whole point of this video is to reawaken those pathways to the knowledge that you did save somewhere in your brain from last year. All right, at what point does this function have a horizontal tangent line? You know what, you are free to write that down and do it before and pause this video. I'm going to go ahead and show the answer. And so what we're looking at is we are forced to use the quotient rule, unfortunately. I mean, it's not that big of a deal, right? But we find the derivative, and then we know that a horizontal tangent line would have a slope equal to 0. So when we find the derivative, what we're really finding is the equation that will give us the slope of any tangent line to that curve. And so the tangent lines to the curve that are horizontal obviously have a slope of 0. And I probably wrote all these things down, right? Oh, darn, all these zeros. I hate when, right, we do all this hard work and both of the answers, x and y, are both zeros. It happens. All right, if you want to pause and find the second derivative of this function, I would go ahead and do that and write it down. And here we go, looking at the answer. Not sure what's going on with this purple. There we go, we can see it better. Okay, so this is just breaking down how I solved it. Once again, pause it, and I am moving on so that it doesn't seem like the video is as long when someone first clicks on it. All right, and then in section 2.4, I'm not sure why my sections are way down there. 2.4, we've got the chain rule. I'm going to go ahead and show you, let's see, which one should I do? Let's do this one first. When we're given this function, first I'm going to rewrite it so that we have a fractional exponent, right? It's hard to take derivatives with the root. Well, it's not hard. We just can't do it. So we're going to rewrite first, and then we go through using the product rule because we don't have an option, right? And so I remember when I used to teach honors pre-calc that the hardest thing was, let's see, from this line to this line, trying to figure out what exactly we should pull out as the GCF. And so that's a lot of fun, right? Once again, the algebra for some of us is going to be the issue in calculus. So here with a trig function, we want to remember here especially to reposition the power of the 3. Whether you put your 3 here or your 3 here, it means the same thing, that the function itself is being cubed, obviously not the 4t, not the angle. And so when you move it to this position, then it makes it easier to take the derivative. And don't forget to go back in. Once you take the derivative of sine 4t, you go back in, which is obviously cosine 4t, but you go back in and take the derivative of the angle itself. Derivative of 4t is 4. Awesome. Once again, feel free to stay on this page. We're moving on. All right. Then we go to implicit differentiation. I'm not sure why my screen's kind of not showing all of it, but this is section 2.5. And why do we do implicit differentiation? Well, we have to learn about it before we can do related rates, right? When you're taking the derivative of, so far we've been taking the derivative with respect to x, which is awesome, but then when you start taking the derivative with respect to something else, like time, when we do related rates, we need to know how to do implicit differentiation. So here we go. Let's see, right now, y is isolated, so we're finding the derivative explicitly in this first example. So that's what we've been doing up to now. We've been finding the derivative explicitly, but now we're going to be introduced to something called implicit differentiation, because let's look at this right here. We can't isolate y. We don't have a choice, so we have to learn a new way to find the derivative. And so ultimately, we're still taking the derivative of every term with respect to x. So what that means is, as we go through and we see the y cubed, we're going to take the derivative first as if it's an x, as if we're our normal way of taking the derivative, and that would give us the 3y squared, but we're really taking the derivative of y with respect to x, and that's why we add this. That's what that says, the derivative of y with respect to x. So we go through each term taking the derivative of y, and this pretty much just sums it up. Every time you're going to take the derivative of a term with a y in it, oh no, that does not sum it up. Now it's summing up this second term, third line. But anytime you take the derivative of a term with a y in it, you're going to tack on the dy over dx. Once you do this, when we're moving on to this section, you want to go ahead and kick the 2x over to the other side so that every single term that's left has that has the dy over dx included, and then you can factor it out and find the derivative of y with respect to x. Let's see what's behind here. Oh, okay. I like this is another take on it. Taking the derivative implicitly, it's just like using the chain rule, because when you take the derivative of y to the fourth, you're taking the derivative right away, which is 4y cubed, but then you go back into the y. So you take the derivative first of y to the fourth, and you go back in and take the derivative of y with respect to x. Okay, let's look at another. Okay, this sums up what I was saying every time, right? You take a derivative of a y term, you must attach a dy over dx. All right, so let's look at some examples of taking the derivative implicitly. Once again, I could have backed it up, right? No, go back. All right, let's see. Let's go ahead, if you want to challenge yourself, write that down, take the derivative implicitly, and then go ahead and see if your answer looks like my answer. Okay, hold on because I have people talking, and so hold on. Okay, and I'm back. They were two people were talking at the bottom of my stairs about replacing the carpet on my stairs. So awesome, but I couldn't focus. So let's go ahead and look at this second one. Let's see if you can find the derivative implicitly and at a certain point, 0, 0. So challenge yourself, pause the video, come back, and there you have it. So hopefully, my hope is that you're going to be good on some slides, and other slides you're just going to have to pause and work through the lines. So here we go, we're going to keep going. And we are now at related rates. And so I think a good intro to related rates, I know you've seen it before, you don't need the intro, but think about water leaving a cone and how all of the rates of change are related. The changes in volume, height, and radius are related, and it's all changing with respect to time. And so once again, we're going to go ahead and do derivatives. We're going to take the derivative implicitly because we are taking each derivative, we're taking the derivative of each term with respect to time. So let's go ahead and see what's behind 2. Let me see if I can pull this down. Okay, so, oh man, let's see if we can go back and do that again. So if you want to challenge yourself, pause the video, see if you can figure this related rates problem out and then come back. That would be awesome. Otherwise, okay, here we go. Read the problem first, then see if you agree with the given and the find. So go ahead and do that, and then come back and see how I worked it out. So the steps are outlined. The first step really isn't find a formula. I think the first step is there we go. The first step really should be this: find the given and find what they give you and what you need to find. But also finding a formula, you may sometimes have to actually draw a picture to figure out what kind of formula you need, but we need to start with a formula. And so once you have the formula, you're just going to take the derivative implicitly, reminding yourself of what you are solving for. So when it says at what rate is the total area changing, we know that's the derivative of A, right? So we found the derivative of A, the area, with respect to time. All right, let's look at some more examples. All right, here we've got air being pumped into a spherical balloon. So once again, well, I did not do the given and the find, but I started with a formula, took the derivative, etc. All right, read right after reading through this problem. Okay, so let's see what this problem says. All right, so go ahead, pause, read what the problem says, and let's see what I have behind this. Let's see. Okay, so there we go. I finally caught on that the reader or the watcher of the video might need the given. So when you read through this, what are they giving? They're telling us that y, now I changed y, I think it had it as something else. I might have had it as S, and I can't stand S's because they look like 5s, right? So y is decreasing at a rate of 400 miles per hour. Whenever we see rate, and we see that 400 miles per hour, but also the decreasing is going to give me a negative. That is our given. The y is changing at a rate of 400 miles per hour, and it's decreasing, so that's why we have a negative. And that is happening when y is equal to 10 miles. So that was our given. And then we want to find the speed of the plane, and obviously we track speed by how quickly this plane moves through the sky, but we can only track it from one point to another that's on the ground. So that's why x is going to represent the distance, and dx over dt is going to represent the speed of the plane, right? The derivative of the distance is the speed. All right, so let's see what I have down here. Decide what formula works with the situation. Realize that we were given a derivative, so this is different. We weren't given a derivative, unlike the first problem. So go ahead once again and pause. Some of you are like, got it. I think we realized too in the red that we had to go ahead and look at the triangle and know, hey, what is x when we're looking at y being equal to 10, because that's what we were given. So we had to use the right triangle and Pythagorean theorem to find that x is equal to 8 when y is 10. And we used that We plugged an 8 in somewhere. Oops, there it is. It's a 16. So there we go, right? I'm one step ahead of myself. We plugged it in right there. 2 times 8 is 16. All right. Once again, if you're going through this and you're like, this is great, except for on this part, I don't have a question on this problem, please come into class and ask me. Okay, another related rates problem. Let's look at what we have. Let's see if we can pull down and look at the problem first. We kind of need the whole thing, don't we? We need the picture as well. So here's another one that involves tan. And so just looking at this problem, we realize that we've got SOHCAHTOA that's involved. We also, because right, tan's going to be the opposite over the adjacent. How do we get that the adjacent was 2,000? We went ahead and did our work right down here. So that's that. So lots of little side work here, and that's a typical related rates problem. And once again, do we do our find, our given in our find? I'm not sure. Let's see what I have behind here. All right. All right. So this is actually brings it all together. How are we going to be successful at related rates problems? Well, first of all, we have to memorize some formulas, right? Some basic formula of volume and area. Of course, the Pythagorean theorem we could recite in our sleep. The right triangle trig, the SOHCAHTOA, that's what I'm referring to. And then trig in general, unit circle identities converting, implicit differentiation, and substitution, which we did quite a bit of. But most importantly, we have to be willing to make mistakes, and that's at the very, very bottom. But I think with related rates, I don't know about you, but sometimes I read them and I'm like, what? And I have to draw my picture, and I have to think, and if I feel pressured to come up with an answer right away, that just makes everything worse. So what I do is I'm like, you know what? I'm willing to dive in and make a mistake and then go, wait a minute, that doesn't seem right. So I hope you can be the same way as well. And I know that when we're working together, either with one student or in a pod with 3 students, some people's processing speed might be faster than ours. And that's okay. Processing speed is independent from IQ. And we can work together in ways that works for all of us. So that's the first thing. Please be willing to make mistakes. We don't have to be perfect. We're human. We're not going to be perfect. All right, so let's go back up here. Reading the problem thoroughly. That's also just slow yourself down. I'm a fast processor too, and sometimes I need to slow down. Drawing a representation. That really helps me list the givens. As you can see, I'm not that good at that. I probably need to slow down and do that. And then, of course, identify what we're solving for and what formula brings the given and the unknowns together. That's really big. All right, I think that's it because chapter 2 ended with related rates. And it did. I've got some extra stuff there we don't need to pay attention to. So I hope you enjoyed this video. I hope it brought back some great memories, and I look forward to working with you in class. Thanks for joining me.